So I first of all thank Professor Michel for having invited me to deliver a couple of talks. So the topic has been chosen by him, and it is something which is very dear to me too. I have been looking at some of these texts which deal with science for almost 2 decades since I completed my postgraduate in physics. And what really fascinated me was the amount of science that has been done in the form of verses in Sanskrit. Of course, from my childhood I had the opportunity to study some of these philosophical texts, religious texts, etc., which are in Sanskrit, and hailing from a very traditional family, I also learnt Veda from my father, grandfather, and so on. So I knew there is a lot of literature in philosophy, there is a lot of literature related to religious rites and so on in Sanskrit, but I never knew that there is a lot of science in Sanskrit also. I mean, to be frank, till I completed my postgraduate, I had absolutely no idea whatsoever. But then, so strangely, I was drawn into the study of history of science, and with the background of Sanskrit, I could not make much progress even with some of these texts. So though I had a very solid background, but then, so we all know that technical literature is technical literature. Just because someone knows English, he cannot understand chemistry or physics, and so too is the case with astronomy or mathematics if one wants to look into these Sanskrit texts. And one of the very interesting features which I came to know when I started looking at some of these astronomical texts is that they have been able to very beautifully codify whatever be the kind of formula that they wanted to bring in the form of verses. So why is it that people have been trying to compose in the form of verses, Sanskrit verses in metrical form? Is it something which was compelling them to do so, or is it by choice that they did? So if one looks at, it seems that there were 2 factors. One is, if you want to make something which is far more interesting, so then poetry is a much better medium than prose, right? So the medium is as beautiful as the content that you want to convey, and therefore they would have chosen this. But there was also a compelling reason, I would say. In those days, people had to memorize things. So it is not that they had all kind of media for them to jot down something or record something. So they more or less used their own intellect to memorize things, and therefore poetry would have been a much better form than prose, and therefore they had chosen this poetry, metrical composition, to convey all of them. And what is interesting to note is not only the formulae which were quite intricate, which were composed in the form of verses, but even the proofs were also written down in the form of nice verses. So if you just keep following the verses and the kind of prescription that is given, so you will be able to arrive at some very interesting proofs. I will try to demonstrate as to how they have done it with 1 or 2 examples in various cases. Here I also wanted to highlight, so one of the observations which was done by this Mumford is a Fields medalist, as you know. So he says rigorous mathematics in the Greek style should not be seen as the only way to gain mathematical knowledge. The muse of mathematics can be wooed in many different ways and her secrets teased out of her. So this is a very interesting observation which he makes. So it is in connection with trying to introduce Indian mathematics. So he makes this observation, and he has been interested in history for a long time. So having studied history of mathematics for quite some time, so he makes this kind of interesting observation, and this is something which I also realized, so as I have been dwelling on it for quite some time. What is interesting to note is the same result has been arrived by different civilizations, but the approach has been completely different, and sometimes even the purpose has been completely different. So this is something which is very interesting. As anybody who is interested in science, if we can arrive at the same result by different methods, we will be really excited. So that is something which is worthwhile in studying this. See, sometimes there may be something which you will find which is unique to this tradition which cannot be found elsewhere. Sometimes you may find some algorithm which is far more efficient than the existing algorithm elsewhere in Indian tradition. But even if you do not find, I would say that these are something which is worthwhile investigating because it excites you. So it is really fascinating to understand how different civilizations have approached this problem for different purposes and arrive at the same result in different ways. So that is what I think in essence he is trying to convey here. But unfortunately, so we have not been able to enjoy or appreciate any of them because all of us are trained in a particular way and our approach has to be unique. That is what our system demands. Okay. He also makes a very interesting comment right at the beginning of a detailed review that he writes on a particular book. So I just wanted to highlight this for two reasons. One is, so he is trying to list a few things which are considered to be hallmarks in the development of mathematics. So he lists, so this particular thing, the Pythagorean theorem, see, this has been known to Vedic priests around this period, and then he says around the 5th century they have arrived at the sine function in the connection with sine function, the differential equation in its difference form. Okay, so this is Aryabhata's thing which he is referring to. This is around 5th century, and then of course this is another thing. So he has not listed certain other things which is fairly well known like zero, decimal place value system, algebra, and so on and so forth. But these are certain interesting things which he lists here, and so he says that see, this is something which many of us do not know, and if you want you can just look into this text. Let me straight away give you a flavor of what I mean. As children, when we study in schools, we are supposed to memorize various formulae, and these formulae are not retained by us for a very long time. So even if they move out from one class to another class, when I ask a particular formula, many of these children do not even remember what they had read. But remembering certain formulae is something which is quite useful for various reasons when we want to apply it in various contexts. And here, even this, the surface area, volume of a sphere, etc. So there is a very beautiful verse which we find in Leelavati, wherein he gives in one stroke the area of a circle, and then the surface area of a sphere, and also the volume of a sphere. So it has been very beautifully codified. Vrittakshetre paridhigunitav vyasapada phalam tat kshunnam vedair upari paritaha kandukasyeva jalam golasyevam tadapicha phalam prishthajam vyasanignam shadhir bhaktam bhavati niyatam golagarbhe ghanakhyam. In fact, this has been, I don't know if any of you have heard about this work of Kalidasa Meghaduta. So he composes in what is known as Mandakranta meter. So this has been composed in Mandakranta. Vrittakshetre paridhigunitav vyasavada phalam tat kshunnam vedai. So it has a very nice rhythm. So this author chooses various meters for various purposes. The phalam here means basically area. What he says is Vrittakshetre paridhigunitav vyasapadaha. Vrittakshetre, vritta means circle. So if you conceive of a geometry which is circle in nature, if you want to find out its area, so it is expressed as circumference times diameter by 4. So we study as pi by pi times r square. So this pi is of course the most mysterious number, but circumference is something which is known as a sort of a geometry, and diameter is also something known, and he presents it as circumference times diameter by 4. If one thinks of little more deeply, why is it that they express it in this particular form? So it has to do with the most general sense that one gets. So if you want to find out area, you have to multiply length times breadth. So you multiply one with the other, you will get the area. So here it is in the same sense. So this is something maybe little later I will show you. So how it can be very easily demonstrated. So to show that, see, one can very easily appreciate that c times c, suppose you take a circle, divide it into half. So then from the center, so you just draw, conceive it to be made of various triangles, split it out. So what you will find is a sort of conical structure, right? You split. So that will be c by 2, this will be d by 2, multiply them. So you just put one into the other. So they will fit into more or less a rectangle, and therefore you can see that it is nothing but c times d by 4. So this is the way. So the point is, so there is a very interesting way of conveying the result, and this is one thing. Then immediately he says Kshunnam Vedairupariparitaha Kandukasyeva Jalam. So in order to give a feel for what is surface area, so normally when we introduce the spherical polar coordinates, so you draw a sphere and then we conceive of various latitude circles, longitude circles like Earth. So and then we try to do that. So similarly he is giving a nice simile here. Kandukasyeva Jalam. Kanduka means ball. So you can conceive of determining the surface area of a sphere by assuming that there is a sort of net which has been spread on that. Okay. So that is the kind of simile that he gives. Kanduka Jala means net. Kshunnam Vedaihi. I will come to this. So this Veda here refers to number 4. See, the Sanskrit language has had a lot of advantage in trying to represent numbers, particularly in those days. See, when the knowledge system has been transferred from generation to generation orally, so it is always convenient for you to have a different way to remember numbers. See, to fit a particular number, see, number can be, at least there are 4 ways in which numbers can be written down in Sanskrit. So one is, so like 134, suppose you want to say Chatustrimshaduttara Ekashatam. So this is one way of putting it. So word numerals. So another system has been developed which is called Aryabhatan system, which is a very efficient system in a particular sense, but that has not been adopted for some reason which I will try to tell you later. And there is another system so which has been developed wherein you ingeniously make use of the alphabets to represent the numbers. Okay, ka, ka, ga, gha. So you have a sort of mapping between number and that alphabet. So and then you try to represent it. This has a lot of advantages. And there is one more system which they have called it as Bhuta Sankhya system. So this is quite natural. Bhuta Sankhya is, Sankhya is number. So you think of certain things, certain elements, and these elements, so you know that they represent a particular number. Suppose I say ice. Ice represents the number 4, and when you say Veda, Veda represents number 5, so on and so forth, right? So this is Bhuta Sankhya. So suppose you say senses. So then immediately one comes to know that there are 5 senses and therefore senses will represent number 5. So that is a kind of system. So here when he says Kshunnam Vedaihi, Veda means 4, when this particular result which you had got is multiplied by 4, that will give you the surface area. See? Then Prishtajam Vyasanighnam Shadhir Bhaktam Bhavati. So then the area of a sphere multiplied by d by 6, that will give you the volume. So Ghanakhyam. So in one single verse if you memorize, so it is there with you forever. So all the 3 formulae along with some nice simile, and you will never ever forget. Okay. So this is something which is very special, and this language actually so gives you the facility to express. So which you will realize as I give you a few more examples, you will see how beautifully words can be coined, so which represent the theme, etc. One more example. Yes, please.
Any insights into the area of the sphere or the volume of the sphere, like the feeling of it?
Very good. I will just tell you. In fact, I am going to do it a little later to give you a feel as to how the proofs are presented in a much more insightful way than trying to abstract it as we do it. See, today when I teach, so some of this vector calculus. So if you want to introduce, many of the students have this problem of imagining the elementary area, elementary volume, and so on and so forth. Here it is presented in a very beautiful way. Yeah. Okay. And in fact, most of these results when I find, see even, so I may touch upon this little later, so the infinite series for pi by 4, which is normally called Gregory-Leibniz series, the proof ultimately boils down to using this Pythagorean theorem or Sulva theorem and the similarity of triangles, nothing more. And of course, summation of numbers. These are the 3 things which goes in. So if you try to break down, so it is what it boils down to. Okay, so this is another thing which I thought I will just see the facility with which they can represent interesting formulae, which is otherwise difficult to remember. So in the form of verses, this is something which is very brilliant. See, so it is also a very beautiful meter. Saika pada ghana padarthamathaika dyankayuti kila sankalitakhya sadhyutena padena vinigni syatri hrita khalu sankalitakyam. The very name that they have given, see this Sankalita, Sankalanam means putting together. So when you put numbers together, so you want to sum up a certain geometric series, arithmetic series, so it is called Sankalita. Okay, so you sum up all them and then tell what is the total number. And this is the formula which all of us study. So this is first order. So 1 plus 2 plus 3 and so on up to n. And this he is saying pada means number n. Okay. So padam basically means the number of steps. Suppose you have n number of terms in the series. So that basically tells you the total number of steps. Pada means steps. So pada is used to refer to number n. So saika pada means 1 added to n. Then what is to be done? Saika pada ghana. Ghana means multiplication. Padardha is n by 2. Saika pada ghana padardham. So that is all n. So n plus 1 into n by 2. So that gives you, what does it give you? So ekadyanka yutihi. Anka yutihi. Anka is numbers. Yutihi means sum. Ekadi means starting with 1. So starting with 1. So if you have n numbers, then this is the sum. So this is what he says, Sankalitakhya. It is called Sankalita. Okay. So this is what Sankalita. Then you want to go to second order sum. So then what is to be done? See, he says, Ta dviyutena padena vinighni. See, dviyutena padena. See, add 2 to n. Okay. Multiply by that. So n plus 2 should be multiplied. Then 3 hrita means divided by 3, kalu sankalitaikhyam. So this is second order, and then you go on. And in general you can say, so what is the nth order? So all that has been presented, and as soon as they give a particular formulae, so what is found in Sanskrit text is, so they also give you a very beautiful simile wherever it is possible, and immediately some interesting example which has some practical application in your day-to-day life. So here we find a very interesting problem which is given. See, so using this summation. So one may think, I mean, what is the point in finding all the sum and then find what is the formula? Where is it going to be applied? So it is applied in population studies. Okay. So he gives the example: Prativarsham gauhu sute varshatritayena tarnaki tasyaha vidvan vimshati varshaihi gaur ekasyascha santatim kathaya. Assume that you have a nice cow, and this cow, so is taken for granted that it will live for 20 years, and this cow will produce an offspring every year, one female cow. So that cow after 3 years will produce. Okay. So then after 20 years, so what will be the total number of cows that you will have? So tarnaki means, so daughter. Okay. Tasyaha tarnaki. So then it is basically a sum of sums. See? So the answer will be something like 2700. Okay. So that is very interesting application of this. So if you know the formula, you can straight away get this. See? Otherwise you will keep guessing, you will not arrive at the result. So it has a very practical application. So these things are also presented. And this is another verse which I wanted to tell you how some philosophical concept is taken to explain a certain mathematical concept. See, for instance, so we know that these are very difficult things for people. Apparently, none of us think so deeply about 0 and infinity. So when one starts thinking deeply, so they are quite bizarre concepts. See, it doesn't just like that. So number 0 and infinity. In fact, there is an interesting book so by Charles Cephei. So he is an American author who has written quite a few books, and he says 0, the biography of a dangerous idea. Okay, so he presents it very interestingly. Anyway, the point I wanted to convey is, so once you have 0, this infinity cannot be separated. So they two sort of go together. Okay. So and of course the concept of limit also comes in when you deal with them. Bhaskara Acharya, so when he wanted to introduce the notion of infinity, in the context of dividing by 0, when they describe arithmetic operations. Incidentally, let me tell you, the first person to describe arithmetic operations with 0 is Brahmagupta. So before that we do not find. Okay. So the number 0 and arithmetic operations with 0. So he was in 7th century, beginning of 7th century. He has a few verses devoted exclusively for this. What happens to that? In order to explain the concept of this infinity or infinite, so Bhaskaracharya gives this verse. So this is from his Bija Ganita. He says, Asmin vikara khaharena rashau api pravisteshvapi nisriteshu bahushvapi syad laya srishti kale anante achyute bhuta ganeshu yadvat. So he says, this quantity which is obtained by dividing by 0. So how do you describe that quantity? We have a nice way in Sanskrit. So this is how this language helps you very beautifully. They say khahara. Khahara, hara means division. Kham is the word which you use to refer to space. So space is empty and therefore it represents the number 0. In Bhuta Sankhya system, like Veda is 4, so kham means 0. So khahara is a quantity which is obtained by dividing another quantity by 0. Okay, the result obtained by dividing a quantity by 0 is what is referred to as khahara. Okay, so this is a very nice term, short term. So he says, Asmin khahare rashau vikaraha nasti. Rashi is some number, some magnitude. I will not be able to say what the magnitude is. The magnitude is khahara. In this khahara magnitude, there is absolutely no change. Vikara means change. Asmin khahare rashau. So in the quantity which is khahara, there is no change. Khahare rashau vikaro nasti. Asmin vikara khahare narashau. Vikaro nasti, how is it? So any number when added with something or subtracted from something has to have some change in its magnitude. So he says, api pravisteshvapi nisriteshu. Bahushu. Pravisteshu means when something enter into it, which means added to that. Nisriteshu means something which is going out of it. Okay. So api pravisteshu nisriteshu. Whether you add something to it or you subtract something from that. Is it a small magnitude that I am talking about? No. Whatever be the magnitude that you want to add to it or remove from it. So that is conveyed by saying Bahushvapi. Bahushvapi syad laya srishti kale. Now he brings in a certain simile to make this concept to be much better appreciated. So people have been studying this philosophy also along with this. So he brings in an analogy from the philosophy. Sorry. Anante achyute bhuta ganeshu yadvat. When is it? Laya srishti kale. So in this tradition, so this universe is something which is taken to be so changing, ever changing. At one point of time there will be laya of everything and udbhava of everything at a certain point of time. In other words, I mean they have a certain concept of everything becoming unmanifest at a point of time, and then they get manifested at a later point of time, and the manifestation is something which is continuous in nature. Anyway, so that going to unmanifest state is called laya, and coming to manifest state is called srishti. He is saying laya srishti kale, say, of this universe in the laya or srishti, at that point of time. So here this in philosophical literature you will find a certain concept called Sat or Brahman, so which is described as unchanging forever. Okay. So as that infinite is something which will be unchanged by this laya or srishti, so too this number khahara will remain unchanged by something which gets into it or moves out of it. So this is a philosophical simile which is employed by, later I will tell you, so how mathematical principles will be used to describe some philosophy. So this is a very beautiful verse, so which is able to nicely explain the concept of this. And I just wanted to show this. See, India never had the fear of infinite or void. So in comparison with Greece, he says it is primarily because of the kind of philosophy that we had. So I will just leave this so later for people to see. This is a very, very important contribution which has been made by these Kerala mathematicians. So this I am giving you right at the beginning is just to show you See, initially I said, so how the mensuration can be nicely captured in the form of verse, then the summation of series and so on, arithmetic, and then some important concepts. So now I am just telling you a verse, giving you a verse, so which gives you the infinite series itself nicely codified in the form of verse. So this infinite series that one has is this, see, 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. This is an infinite series. So how has this been captured in the form of verse? See, Vyase varidhi nihate. Vyasa means diameter. Varidhi is ocean. See, in the Bhuta Sankhya system. See, so varidhi. See, here the advantage that people have is, this is another advantage of Sanskrit. You have enough number of synonyms. So you can choose a particular synonym, so which will fit into the meter of the verse, and you will be able to nicely compose the meter, and it will never be boring also. See, certain times, sometimes it could be challenging, but certain times it will be very interesting to see another synonym and you will learn. See, there is a nice balance between, see, learning language and employing various meters and so on. These are some very nice things which they have done. And the choice of meter is also something which is very interesting. Once you read a fairly large number of verses, you will also have a feel as to why they employ a certain meter for a particular purpose. And here, what has been employed is Aryavritta. Vyase varidhinihate, Rupa hrite vyasa sagarabhihate, Trisharadi vishama sankhya bhaktam, Rinam swam pratakramat kuryat. Rinam means subtraction, swam means addition. So this is an alternating series. So minus plus and so on. So here he says, so all the odd numbers appear in the denominator. So where is it stated? Trisharadi vishama sankhya bhaktam. So 3 means 3. Shara means bana, okay, arrow. Arrow actually represents number 5. Any guess why arrow is 5? No. Bana is used to refer to number 5. See this in our culture, so we have a sort of divine being associated to most of the things. See, learning means Saraswati. So too we have love means a fellow called Manmatha. Understand? So this Manmatha is referred to as Panchabana. Okay, Panchasahayaka. Why is it? Because if he shoots arrow, all the 5 senses will be lost. You understand? Okay. So therefore this fellow is called Panchabana, and Bana so is a word which is used to refer to number 5. Okay. Okay. In Bhuta Sankhya system. Now Trisharadi, see, etc. So 3, 5, etc. are the odd numbers which go in the denominator. See, Vishama Sankhya means odd number. See, Sama is even, Vishama is odd. So the term also is okay. Vishama Sankhya Bhaktam Rinam Swam Pratakramat Kuryat. See, and Rupa is the word which has been used to refer to number 1. Why? Because the form is unique for every entity. See, you have a unique form, any other being has a unique form. Among the human beings, everyone has a unique form and so on. Rupa is 1. So Rupa Hrite Vyasa Sagara Abhihate. Vyasa Sagara is ocean, Abhihata. See, 4 times the diameter is the numerator for everything, and the denominator starts from 1, 3 and so on. So you do plus minus, you have the infinite series. So this is a remarkable series. So if you look at this mathematical literature history, so Gregory and Leibniz, see, so these are the 2 people who are generally associated with that. So who was the first to discover this? So there was a lot of discussion which went on, and so they decided, so let us give both of them the credits. Okay, so Gregory Leibniz series. But then, so it happens that it has to be assigned to Madhava, so because this is at least 300 years before they discovered this. I mean, if historically one were to be correct. Okay, so this is how the series goes on. See, and this pi has been expressed before this in various other forms, and I wanted to give you these 2 verses to tell you how the numbers have been so beautifully represented by different systems. See, this itself is a very, very interesting thing. So if I were to show you how important it is to represent numbers in a very convenient way, we will be able to appreciate it only when I try to perhaps tell you how it has been represented. So if you recall rather this Roman way of representing, okay. And suppose we have pen here, okay. Okay, suppose you wanted to multiply say 48 by 27. So if one were to write it in Roman system, so 48 will be 1, 1, 1, 1, 1, 1, 1, right? Yeah. We will have V also in between. And then this has to be multiplied by some other number. See, now what we do is we just very beautifully do it in no time. So in this kind of representation, so it is extremely difficult. So in the Roman system is anyway, so abandoned completely, right? So it is something which is not at all viable or easy to do any kind of computation. Even with large numbers, suppose you want to do representation, it is going to be extremely difficult. So how many characters do you need? And it will take long time for us to even read that, right? Suppose you want to represent 43,28,000. So there it's extremely difficult. So here we have a beautiful system which has been adopted. Of course, the decimal place value system is one aspect. Representation is a completely different aspect, and particularly when you want to put it in meters is a third aspect. So all of them is very interesting to note here, and Sanskrit so has provided both alphabet as well as various other things that you have, has provided very easy way, and they have done it in a very, very beautiful way. See, I'll tell you that in other aspects, the language is so rich that at a certain point of time, so people have been able to compose verses which have completely different meaning when you read as a pure Sanskritist, and when you want to read it as a mathematician, you will get a completely different thing. See, Sanskrit as a language of science has been made use of in such a way. See, that is actually very useful for you. See, for you, if you want to represent some numbers, or rather a series of numbers, okay, so you want to make it for some reason. Suppose you want to construct sine table, you want to represent so certain other things. So there is something called Vakya system of representing the longitudes of planets. So there, all that they have done is they have composed very nice sentences, so which will either convey you some moral value or worldly wisdom and so on and so forth. So you read this, so you will appreciate it for some other reason, and by memorizing them you will turn to be a much better person, because you know a lot of moral values and worldly wisdom which have been conveyed through them. But you will also be able to compute so various longitudes, latitudes, etc. So that is another thing which the Sanskrit language has provided us. Okay. So if you by using alphabets, by combining them in a particular way. See, for instance, let me give you one simple example straight away. See, so they will say Girna Shreyaha Dhenava Shrihi. See, these are all some short sentences. So sometimes you can have longer sentences and so on. So Dhenava Shrihi, so what do we understand? Dhenuhu means cow, Shrihi means wealth. So cows are our wealth. Okay, but then when you try to decode it using Katapayadi system, see, so Dha is basically 9, see, Na is 0, Va is 4, Shri is 2, so this goes to 24 degrees 09 minutes. Okay, so you put it the other way around. So there are a lot of sentences like this, and these sentences, so, and sometimes people have gone to the extent of composing them not as individual sentences which are meaningful, but a story can be narrated. See, this develops the language skills of a person, and it also adds beauty to the literature. See, so you can at once learn a certain story, and you can keep doing certain astronomical computations. See, these are all some interesting aspects which one finds, and I don't think it is easy to do such things in any other language. Okay. Vyase Varitini. See, this is something where Aryabhata for the first time gives the value of pi correct to 4 decimals. So what I wanted to say here was, so we have this Ayuta Dvaya Vishkambha. See, Ayuta is the term which is used to refer to 10 to the power of 4, Dvaya is 2, Vishkambha is diameter, and here he has used Chaturadhikam Shatamashta Gunam. Dvashashtis Tatha Sahasranam Ayutadvaya Vishkambhasya, and the same thing has been conveyed in a different way. So using this, see, Ka Bana Suryaihi, Ka is 0, Bana is 5, Surya is 12. So this is in Bhuta Sankhya system. So they have been able to compose very nice verses. So here comes another interesting verse. This is supposed to give you the value of pi correct to 11 decimal places. How has it been composed? So if you, in fact, I don't know if you have looked into an interesting verse which has been composed recently by one Bharati Krishna Tirtha. There, so the example which I was giving you, so you can construct a verse. Okay, so the verse has 32 syllables. The simplest meter, one of the simplest meters is Anushtup Vritta. Okay, Bhagavad Gita is more or less in Anushtup. Ramayana is also in Anushtup. So Anushtup meter has 8 syllables per quarter. Totally there will be 32 syllables. For instance, Karmanyevadhikaraste ma phaleshu kadachana. 16. Ma karma phala heturbhuhu ma te sangostva karmani. Okay, so there are 8, 8, 8, 8, 32 syllables. Each syllable will represent one digit. So this person has composed a nice verse. Gopi bhagya madhuvrata shingi shodadhi sandiga khalajivita khatava galahara lasandhara. So this is a nice verse which has a different meaning, and if you want to decode it, this will give you the value of pi correct to 31 decimal places. It's 3 plus 31 decimal, there are 32 syllables. So these are the ways in which this language can be made use of because of the flexibility of the Katapayadi system, which gives you a way of representing numbers. Okay, so this is a beautiful blend, but here he has used what is known as Bhuta Sankhya. Vibudha Netra Gajahi Hutashana. Vibudha is 33, Netra is 2, Gaja is 8, Ahi is 8, the serpent, Hutasha is 3, fire. See, those days they used to have Tretagni. See, so 3 fires will be there. Ahavaniya, Dakshina, Garhapatya. So therefore fire is the word which is used to refer to 3. Similarly, Guna will also be used. Sattva, Rajas, Tamas. Okay. So these are all certain words which are employed to refer to numbers. So this is the numerator. This first half gives you the numerator, and Nava Nikharva. Let me just tell you, this powers of 10 have different names. In the modern system, we have million, billion, trillion, and then we have only names for. But here they have given. So every power of 10 will have a name. So Nikharva refers to number 10 to the power of 11. Nava Nikharva. Vriti Vistare Paridhimanam idam Jagadur Bhutaha. So this is a verse which is usually ascribed to Madhavacharya. But what is interesting to note here is this last thing. Jagadur Bhutaha. Madhavacharya Muktavan, he says. Madhava has said this. Madhava has said this means this verse says as if it has been given by somebody else. I don't know. So Budhaha Jagaduhu means wise people say. Wise people state this to be the value. So this is ascribed to Madhavacharya. So whether it is Madhava's own verse or is it something which goes before, we have absolutely no clue from this verse. But definitely Madhava seems to be the pioneer as far as we know, based on the literature that is available. Anyway, so this I wanted to give you to make you have a feel as to how you can compose nice verse to remember the value of pi correct to 11 decimal places. See, so this is how it goes. Jagadur Budhaha. But unfortunately, this is one thing which I thought I will incidentally insert in. Okay. So this verse which I quoted is so well known, and some author who writes in 2010, okay, a book. So he says for 2000 years the only way to pinpoint pi was by using polygons, but in 17th century Leibniz and Gregory ushered with a new age of pi appreciation with the formula. See, this cannot be certainly due to ignorance, right? In 2010, somebody authoring a popular book, and this person in fact met me in IIT, and then he interviewed me. So he asked certain questions and then I answered. At the end, he handed over a book and then he went off. So later, after 2 months, I just flipped through the book and I was really surprised to see that after all he has been writing, he has been a journalist, he has been author. So why this kind of suppression, I don't understand. So as if nothing happened for 2000 years. So this is first known that the series was invented by mathematicians belonging to Kerala. It is first known in 1835. Then it did not come out for 100 years. So then later there were a few articles on that, and a lot of discussion goes on. So, and particularly towards the end of 20th century, so many people had written on various things, and this person writes a popular book not conveying the truth, right? So this is something which is very strange. Okay. Why were they first of all interested in inventing different systems for representing numbers? So this is another question. And what was the need for these people to come up with various interesting systems to represent numbers? See, this is another question which comes up to our mind. After all, if you have one system, it is fine. So maybe at some point you develop some notation to represent, that is also fine, right? Here, one of the reasons, not only this, but also for various development in mathematics which took place. It seems to be that they were very seriously concerned regarding the accuracy of the planetary positions which they can predict. So every astronomer, every king will have some astronomers in his court. Okay, so the best astronomer will be brought in, and then they will be honored, and so on and so forth. It could be for various reasons, not necessarily so religious purposes. So you want to know when a particular season will begin, when a particular thing has to be taken, and so on and so forth. Or it could be out of sheer curiosity as a scientist, if I can predict eclipse, so let me throw a challenge upon you, whether you will do or I will do, right? So sheer intellectual excitement. So these are all certain challenges which these people had. And if you want to do them, so then obviously you should have a certain mathematical model, and any mathematical model that you do for any system, sine function will come, right? The sine function is ubiquitous. So this is something which they have encountered, and if your model involves this, so finding sine and sine inverse, then obviously you should have a very accurate way of determining for any particular angle. So this seems to be one of the preoccupations which these people had, and they had various methods for determining sine. So these are all some interesting things. So they had come up with different kinds of recursive relations, not necessarily one. So the earlier thing, when I quoted Mumford, so I just said, see, the differential, so difference form of the differential equation for sine function, this is one way. There are other ways in which they have done, so very interesting recursive formula, so which I may not have time. So, but I just tell you, but they have done very interesting ways of determining sine function. So, to any sort of given accuracy at a later stage. So, they have, but it is always convenient to use a table form, see, rather than trying to find out using a formula for every thing. So, that is what we used to do. And even today, so to a desired accuracy, you can always feed in. See, you can construct a table. So if you want 5 decimal places accuracy, then 7 decimal places, then you have to have a different kind of a table, which you will try to make use of. So that seems to be one of the driving factors so as to when these two are in conjunction, and these two are in conjunction whether there will be eclipse or not, and so on and so forth, right? So this is also moving at a varying speed. The other thing is also moving at a varying speed. When will they meet each other, right? So these are interesting problems, and this will be the way to keep track of day also. See, for instance, suppose there is a conjunction of sun and the moon, so this will be a new moon day, right? So this fellow goes here and is exactly opposite, it will be a full moon day. This you divide into 15 parts, and then you could divide into 15 parts. So this has to do basically with the average time taken by the moon to meet the sun. See, the average period will be 29.54 days, see, between two full moons. So that is why they had divided this period into 30. Why divide this into 30? That is the meaning, right? So they had lunar month divided into 30 parts. This has to do with the average time. Sometimes it can be even 31 days, depending upon the rate at which they move. But then the average is 30, and therefore they can say chosen to divide this period to this period as 15, and this to this as 15. So this is called tithi. So when does a tithi exactly end? So this itself is an interesting problem. So from here to here it covers 180 degrees, and this will be divided into 15. So what you have to do is, you have to find the time period taken by the moon to lead the sun exactly by 12 degrees. That will give you the period of a tithi. So you need to know the rate of motion. So the rate of motion, and you have to just keep on calculating. So that is how it goes. So these are the purposes as to why they had to develop various notions, okay, in mathematics. So let me just very briefly tell you that how important it is, but see, this is something which is just taken for granted, the decimal place value system. And place value system, let me tell you, is not only the invention of Indians, so it has been discovered elsewhere also. So particularly one thing which is very famous is this: the Babylonians had this, but they had what is known as sexagesimal system, so not a decimal system, okay. In sexagesimal system, so there also there is a see, let me give you an example, so then we will be able to appreciate this. See, for instance, suppose you have a number, so let us say 4871, this is some number. In our decimal system, so how do we understand this? So we understand this to be made up of, say, 4000 plus 800 plus 70, so plus 1, right? So you just add them, you get this 4871. So all that we need is basically 4 letters. If you want to represent this, you need 4 notations, rather 4 symbols. So decimal place value system has this advantage. You just have 4 symbols, and you will be able to write it depending upon the position. So this picks up a particular value, this picks up a particular value, this picks up a particular value. So all these numbers have some intrinsic value, and they also have a positional value, and it is nicely placed. Suppose I were to represent in this sexagesimal system adopted by Babylonians, okay. So it is sexagesimal. So how do we do this? So here everything actually goes by, suppose this, the first term has to be multiplied by 10 to the power 0, second has to be multiplied by 10 to the power 1, third has to be multiplied by 10 to the power 2, and fourth has to be multiplied by 10 to the power 3, and so on. So this is what we do. In sexagesimal system, so what they had was, there were only 2 symbols which they were using. One to represent number 1, the other to represent 10. So this is what they had. See, for representing 1, so they used something like this, and this is 1, and for representing 10, so they use something like this. So this is 10. These are the 2 things that they have. Suppose in this notation, we were to represent this number. So what is to be done is, first you have to pull out. You understand, here it goes by 10 to the power of n. So there it will go by 10 to the power 60 to the power of n. because it is hexadecimal, right? So 60 to the power of n. So in 60 to the power of 10, so you have to first of all pull out the factor 60 square. So then you have to pull out the factor 60, then whatever remains, right? Here what we did was pull out the factor 10 to the power of 3, 10 to the power of 2, 10 to the power of 1 and 10. So what you have to pull out is something like 3600 will be 60 square, the first thing can come out. Then something into, see, 60 plus remaining, right? So here, so what will remain? 1200 will be there, and see, maybe you can put 21 times 60, right? So this is 21 times 60. So this times 21 will give 1260 plus 11. See, this will give you the number. So this is what, and this you have to represent now. See, in this, the representation is you have to just place one by one. So here with these two notations you have to represent them. So they used to have something like this. See, so this will be there 1. This 1 times 60 square will go plus 21 times 60. 21. So 21 will be something like this. See, 20 and then 1, and then you will have 11. So 11 you have to use 2 ones. Okay. So this times 60 and this times 60 to the power of 0. So this is how the representation. Now you can see, so how convenient it is to use the decimal place value system with the notation. So here also we have a place value system, but then how will you understand? See, so how this separation, see, if you just write it together, then you are confused. So you have to see to it that there is enough separation between them. So otherwise it will be extremely difficult to figure out, so what it is. But to get the number out of it also is something which is somewhat difficult, and there is also a lot of ambiguity here. See. So what will you do to represent 60? So to represent, so if you put this number 1, it simply represents number 1. So to represent 60, you have to put here. But if you simply write this, whether it is 60 or 1 or 60 to the power of n, so that is also, suppose you want to say, so I want to represent 3600. So you have to use only this, and there is nothing to represent 0. The issue is 0, that is why it is extremely important to understand. See, if you put 0, see, the null digit is represented by 0, and therefore there is absolutely no ambiguity or no confusion. So here in hexadecimal system, to represent any power of 60, see, 60 to the 0, you have this notation, 60 to the 1, you have this notation, 60 to the 2, you have this notation. But if you simply write 1, so whether it represents which power of 60, you will not be able to say. So these are certain problems which we have in certain other things. So that is just to, you would have read various quotations about this. So this, the enormous simplification that has been brought out by system in doing arithmetic can never be overstated. So this is something, as well as notation. See, the notation, whether it is in this form or other form, so it is something which is really amazing, and this has been appreciated by various thinkers at various points of time. I will just give a break after giving these quotations. See, the role played by this place value system has been beautifully brought out by this. See, most of the great discoveries and inventions of this Europe is so proud of would have been impossible without the development of system of mathematics, and this in turn would have been impossible if Europe had been shackled by the unwieldy system of Roman numerals. So the unknown man who devised the new system was, from the world's point of view, after the Buddha, the most important son of India. So I mean, he just tries to compare the sheer brilliance, whether it is philosophy or a discovery in mathematics. Okay, so it is in this sense he is conveying his achievement, to though easily taken for granted, was the work of analytic mind of the first order, and he deserves much more honor than so. So this is conveying the importance of this, and so too the famous mathematician Laplace has this the ingenious method of expressing every possible number using a set of 10 symbols, each symbol having a place value and an absolute value, emerged in India, and so on and so forth. So that is how it goes. So I was mentioning about this decimal place value system. So earlier, so in the context of trying to explain the concept of infinity, I mentioned that how a philosophical example is taken to explain the concept of infinity there. So here we find very ancient literature wherein, so people this actually gives us a clue as to how this decimal place value system has been in vogue among the society. So because this philosophical literature, so it draws examples from this. See, yatha eka rekha shatasthane shatam dasasthane dasha eka cha ekasthane. It basically tells you have some notation, and this notation, see, so this 4, if it were to be here, then it is to be multiplied by 10 to the power of 3. If the 4 were to be here, it has to be multiplied by 10 to the power of 2. If the 4 were to be here, 10 to the power of 0. So this is called ekasthana, dashasthana, shatasthana, and so on. So eka rekha means the same notation. So depending upon where you place, it picks up a certain value. So similarly, he wants to explain something in a philosophical domain. And much more graphically, Shankara says, yatha ekopi devadattaha, the same fellow Devadatta, loke swarupam sambandhirupam cha apekshya aneka shabda pratyaya bhag bhavati. In fact, he gives a very nice simile. He says, the same fellow Devadatta. So swarupam sambandhirupam, depending upon the kind of connection that he has with the other people. Suppose you are here as a professor, the student will call you a professor. Your son will call you a father. So your wife will call a spouse. So the same fellow. So he is described in different terms depending upon the connection with this fellow has the other fellow. So similarly, so that is what he is saying. See, Manushyaha, Brahmanaha, Shrotriyaha, say depending upon where he is born, what kind of profession he follows, and what stage of life he is. So he picks up various nomenclatures. So yatha ekapi sati rekha. Similarly, he is saying, see, ekapi sati rekha, the same symbol. See, sthananyatvena nivishamana ekadasha shata sahasradi shabda pratyaya bhedan anubhavati. So when the 4 is here, you describe it as a 4000. So when the 4 is here, you describe as 400. So this is something which has been extensively used in the philosophical literature to explain a certain philosophical concept. So unless the concept is something which is familiar to people, nobody can choose this as an example. So the point I want to drive here is, so this is something which has been extensively employed in the society. And of course, some of the algorithms, so as just we had a discussion, so the algorithms which Aryabhata has presented to do various things, for instance, how to extract square root, how to extract cube root, and so on, it is a very systematic algorithm. So unless one has things in algebraic form, and then so he will not be able to prescribe a certain algorithm to determine the square root. So all this clearly points to the fact that we have been excelling in trying to employ the decimal place value system along with this algebraic equations and so on. Okay. And let me just tell you, this is a very clever way of using our vowels and consonants to represent huge numbers. So this is a very interesting way just to know out of this is the sheer brilliance of this person to make use of vowels and consonants to represent very huge numbers. So this is something which has been done by Aryabhata. But this doesn't have the beauty with which you will be able to compose verses which is quite readable and which can give you a different meaning and also numbers. Therefore people abandon this. But as such, so when you want to think of merely representing numbers, this is something which is a remarkable way of doing. What this fellow did was, so he thought of this way. The vowels basically that you tagged to a particular constant will dictate the power by which you have to multiply by that number. So here, as it is positional, so you can very easily think of, so 4, suppose you have a consonant, let us say va. Va is 4, assume. Now this va, when you multiply, when you add it to a, it will pick up one value. When you say v, va is 4, then e, so you have to multiply by 10 to the power of 2. Suppose you say wu, so then 4 into 10 to the power of 4, right? So you, for every vowel, you shift it. So it is in a sense centesimal system which this person seems to have thought about. See, we deal with decimal, so it goes with 10 to the power of 10 raised to the power of 1, 2, 3. So here a is 0, e is 2, u is 4, and so on, 2 to the n. So that is how it goes. So this is a nice way of representing huge numbers. So this is what Aryabhatta has done, and these are all consonants which take one. See, ka is 1, ka is 2, 3, 4, 5, and so on, 25. So this is how he will do this. So in Aryabhattan system, see, it goes like this. Ka is 1 and it goes to 25. Then what he has done is he has classified. In Sanskrit, this itself is a very beautiful science. See, as Michelle was mentioning just now. So people have worked on it. So where does the sound emerge from? So this has been so thoroughly analyzed in the literature, so linguistic literature. So this also people study during grammar, and of course various other detailed study has gone in. So how do these words combine and how do they generate meaning? This is what is called Shabda Bodha. So there are volumes which have been written. So a sentence is uttered, how do you get the meaning? So there is a very interesting discussion which goes on. Even the words, letters have been very nicely classified so as to which class they belong to. Say for instance aspirated, velar, palatal, and so on. Now, there are various things which have been done. So what Aryabhatta does is, this is like a matrix, see, so 5 by 5. So therefore he called it as a varga. Varga means square. Okay, so we have a 5 by 5 matrix. So this is vargakshara. So ka to ma is called vargakshara, and after that he calls it as avargakshara, ya to ha. So having done this, so he further goes on and then says, see, from a, e, u, r, l, all the vowels, so they go as 10 to the power of 2, 4, and so on up to 10 to the power of 16. Okay. Au, So then he says, there is a nice verse, so which basically describes how one should compute numbers in a system. See, vargaksharani varge, avargaksharani, avarge avargaksharani, kat yaha, khadvinavake swaraha, navavarge, avarge, navantya vargeva. So this is the verse which he gives in his Aryabhatiya. So just at the beginning, as to how, see, this is a very systematic way. So we are, when we write a textbook, we say these are the notations which I am going to use. Right? So it is in that sense, I mean, he says this is the mathematical representation of numbers as far as my work is concerned. So this is what he does it right at the beginning. And here, let me give you one simple example. For instance, Hugh. This Hugh, see, Kha is tagged with, see, Kha, Ya is tagged with Wu. Get it? So whenever there is a consonant without a vowel tagged to it, so it will go to the next consonant which is tagged to the vowel. So here this is to be understood as K, U, U, and then G, R. So how do we place them? So we have to place them, see, because K as well as Ya, both are tagged with Wu, and you can easily have a feeling as to why he had a centesimal system. See, for A, so you can either have a vargakshara or avargakshara. Okay, so therefore you place it appropriately. So varga, avarga. Since Ya happens to be avarga, you have to put it here, and Va happens to be varga. See, Ya, Ka is varga. So this, and then because you have a Wu, and there is nothing like E, A. Yes, please.
So that's how the odd powers have been created.
Correct, correct. See. It's a very interesting question. Just now I said little early, see, the need for this number arises from very simple context. You had to calculate planetary positions, and each planet has its own period. So this takes 88.2 days, the other thing takes 279 point days, and the 576 point something. Now you choose a very large period, and in this large period, this planet makes so many number of revolutions. You put it. So they started with what is called Yuga, Mahayuga, which is 43,20,000. That is a very close period in which they make integral number of revolutions. So you represent the mean motion of a planet from which you compute the true motion in some integer, and all these integers have to be represented in nice beautiful verse format. So you choose different numbers by which you will be able to compose it. So in fact you can have, there are people who have composed one single verse in which all the revolutions will be listed. So it is a Shardula Vikridita. So Shardula Vikridita, sometimes even Sragdhara, 21 syllables. So you memorize one verse, so then you will know what is the mean period of all planets. So you choose a large period, and in this large, see, this is also important for you to specify. See, for instance, if you want to specify what is the duration of a year, to how many decimal places will you be able to state? So it is 365.2584, whatever. Sidereal year is one thing, tropical year is another thing. So sidereal year, suppose I want to say, so then I should have a mechanism. So I will have a large period, and then say in this large period these are the total number of days. So then I will be able to specify. So it is in this context, see, in fact the various kinds of representations seem to have emerged in this. So in this context, whichever is convenient and appealing, so people will choose that. Okay, this is Aryabhatan way of doing. But the problem here is, it will not be easily readable. The readability is lost. Kyugru, for instance, if you want to read Chaya, Giying, Ushru, Chrudu, see, very difficult to pronounce. On the other hand, if you use either Bhuta Sankhya or Katapayadi, so it will be so beautifully readable. So earlier I said Gir Nashreya, Jayanavasri, they are all nice things. So you just place one by one. So here you have to do a little bit of computation, right? Either mentally or physically you have to do that. So because you have to think which has been added to that. But in the other systems you don't need to do, you have to just keep on arranging. Like 4821 you just add, you just put, so each represents one number. So each character represents one number. Here the beauty of this lies in representing very huge numbers using less number of syllables. Suppose you add something which is to this end. See, so suppose you say cow. So cow means 10 to the power of 16. Okay, so that is something which is advantageous here. So on the other hand, if you have to write in other systems, you should have zeros, so many zeros, and then you have to put k, right? So that is the difference between this and that. So it has its own charm and beauty, but because it is difficult to read, people just abandon this. And in fact, this is just you were mentioning about the Rodam Narasimha. Rodam has written an article, and the title is The Terse Verse. Okay, terse verse. I think it appeared in Nature or Science. Nature, yeah. So this, see, this is the verse he does. Maki, Bhaki, Paki, Dhaki, Naki, Nyaki, Naki, Haskas, Kaki. So this is basically the sign table, the entire sign table. Sign table in its difference form. So he doesn't give it. See, so this is the value of sine of 3 degrees 45 minutes. So twice of it you have to add this and that. So this basically gives you the first order sign differences. So you just add it, you will get the sign value. So that is how he has presented the value of the entire sign table in one single verse.
But this table now loses the duality, where the double meaning is gone.
No way. That is the disadvantage in Aryabhatan system. You will not be able to compose it. It will be extremely difficult, and I don't know whether one can succeed at all. So given that you are supposed to add a particular vowel in order to get a value. So there is no issue. See, and putting it in verse form is also something which is extremely convenient with the readability. Okay, so here it is extremely difficult to do that. But another brilliant thing which they have done is, this is something which is noteworthy. So this Makhyadi Rahitam Karma. See, this is Maki, Baki, Paki, Daki. So is one way. See, this, the point is, because you had a nice classification of varga and vowels and all that. So this is one convenient way to represent huge decimal places. It has its own beauty. So let us leave it at that. But computing signs using this is not something which is very friendly. So if you have a way by which you can simply plug in the argument and get the value, that will be very easy. So here if you have any intermediate value, then you have to do interpolation because you list, right? So every 3 degree 45 minutes you list. So I want to get 42 degrees, what do I do? So I have to do this interpolation. Either you do first order interpolation, second order interpolation, depending upon the accuracy of the table that you have listed and the proximity of the values. So that people have done anyway. But then later came this astronomer and mathematician called Bhaskara. So this is different from the 12th century Bhaskara, who is famous for his Leelavati, Bijaganita. This Bhaskara has written independent works as well as a very brilliant commentary on Aryabhatiya, without which it will be very difficult to even understand Aryabhatiya. So here he gives a very interesting approximation, the rational approximation to sine function. So this is not something which is known. So people attempted geometrically determining sine function. So people arrived at analytic equations like the difference equation which Aryabhata did. So they had some recursive relations also. See, let me just write down, so which since a lot of you are scientists here. So there is another interesting relation which these people have written. See, so sine of n theta square minus sine square theta by sine n minus 1 times theta. So this is another recursive relation which is not so well known, which these people have written down. And this is something which I was quite fascinated when I read this. And all that one needs to do is to just play around with the normal trigonometric formula which you usually do. See? So this is like the sine of alpha plus beta into sine of alpha minus beta. See? So that is the difference square, and that is all it is. And the beauty of this is you can choose what people usually do in Indian tradition is, so they don't put it in radians, and therefore they will give it in sort of some other measure. And you can choose whatever radius you want. See, you can say sine 90 is 60. You can say sine 90 is 125. You can say sine 90 is 200. All that you have to do is you have to just plug in and play around. First value has to be determined. So once you know sine theta, you will be able to generate the entire table, and the distance between two values can also be chosen anything. This is another interesting, very nice way of arriving at sine table, which these people have been, and all that it requires is just looking at the Pythagorean theorem, Sulba theorem, and similarity of triangles. That is all. So you will be able to arrive at it. It's a very interesting recursive relation which they have given. Anyway, this is something which is very interesting, and Bhaskara seems to have given this. See, so here khabhreshu khabdhitaha. See, kha is 0, abhra is 0, ishu means bana, arrow, so that is 5, kha is 0, again abdhi is 4, is 40500, and he very nicely puts it. See, chakrardhamshaka samuhat. So 180 degrees is described as chakrardha. Chakra means 360, chakrardha is one half of it, amshaka is degrees, samuhat vishodhyaye bhujamshakaha. So you just have this formula, and this turns out to be a very, very beautiful approximation for sine. So this is how it goes. See, it is almost 99% accurate. This Bhaskara seems to have given this. So he doesn't independently discuss this, neither he presents a method by which he arrived at it, but in some context he casually presents this, and then he goes on. See, he just says chaturthamshena dvishtam antyaphalam, and then he goes on. See, these are the two lines which basically sort of give you this result, 3 lines. So we have no idea as to, but one can find a very easy way by one can arrive at it, see, using some consideration of triangles, similarity of triangles. So one can show that, so this result is obtained. And see, so this is something which I noted. So the Greeks are the first mathematicians who are still real to us today. Oriental mathematics may be interesting curiosity, but Greek mathematics is the real thing. So this is the general impression that one sort of presents in various books. Now I will tell you this briefly how Katapayadi system more or less swept so at a later period. See, almost everyone user started writing using Katapayadi system, the numbers. So here what is done is this simple ka, 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 ga, 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 so it goes up to 0. Then ta you have up to this, and pa. So thus we find for representing 1 you have 4 things ka, ta, pa, ya. So that is why it is called Katapayadi. Okay. So it starts with ka, starts with ta, and so on. So Katapayadi system. So how one should figure out? There is a nice verse which has been written, Nanyavatascha Shunyani. In this Katapayadi system, all the vowels represent 0. Nanyau achascha. See, na, nya, ach is a acronym which is used to represent all the vowels. Why ach is used? Because of the sutras. See, Ayivun, Riluk, Evong, Ayauch. So this is the Maheshwara Sutra of Panini. There are 14 sutras and this is memorized. And these 14 sutras basically give you all the alphabets. The Sanskrit alphabets is presented in 14 sutras. This is what is called Maheshwara Sutra. And why is this written in 14 sutras? And why did he choose to represent 3 in one sutra, 2 in one sutra, 1 in one sutra? This has been so thoroughly analyzed. And some interesting paper I saw, wherein this electrical engineer established that this is the most optimal way. So given that various rules that he is giving later in his work, this would have been the most optimal way of representing these 56 characters or 54 characters in 14 sutras. This study has been done. This is a very interesting analysis which has been done. Anyway, so here in this, all the ach, see, Ayivun, Riluk, Evong, Ayauch. See, suppose I say An, Aivu, Riluk. Suppose I say Ak, Aivu, Rilu. So this is what it represents. This is basically a sort of mnemonic which he wanted to use it later in his work to put things in a precise form. So he has put it in a particular way. That is a very interesting way of putting things, and there are various other reasons why he classified. So here, Nanyau Achascha Shunyani, in this Katapayadi system, so this ach, all the vowels, plus na and cha. See, you look at nya and na, that is 0, plus all the vowels are 0. Sankhyaha Katapayadayaha Mishretu. Suppose you have suppose you had, so let us say Gandhi. Or let us put Gandhi. So what do? So this fellow in is hanging without a vowel. So ga in this, if you go, see, so ga is 3. See, any consonant without a vowel should be ignored. Okay, so only dha will pick up. Okay, so 93 is the number. So you start with the least decimal, so and then reverse it. Okay. So Gandhi. So this is how this goes. So Mishretu Upanta hal sankhya nachavachyo hal aswaraha halaha swaraha nachavachyaha. Anyway, so this is a nice verse which basically describes how the Katapayadi system has to be employed. And there are nice examples. In fact, there is a work called Tantra Sangraha. What people used to do was, they will compose some invocatory verse at the beginning. So it may be on favorite deity, on his own teacher, whatever it is. So this person's favorite deity was Vishnu. So therefore he started with, He Vishnu Nihitam Kritsnam Jagat Tvayeva Karane. Oh Vishnu, so entire universe is in you, kind of a thing. Okay. So you are the sole source of the entire universe and so on, he says. But he has sort of codified the date on which he commenced his work. So this is in Katapayadi. So this turns out to be this number of days. So this days is what is called Kalya Hargana. So from the beginning of Kali, you choose some point of time in the history, right? As this is the beginning of Kali. From then like Julian days. So you start with some point and then keep counting. So that is what they do. So this is something which gives you this number. And in the last verse, he says, Lakshmisha Nihita Jhanaihi. So those who contemplate on Lakshmisha, so what is it that they will not get? Okay. So those who meditate upon that. So there, this turns out to be this. So it just, within the 5-6 days, this person seems to have completed the work. So this is sort of codified. So the point I want to convey here is, this language gives you a certain facility to present something in a particular context, and by the way, you can also represent numbers. So this is the advantage in having. And the other advantage is it's very easy to pronounce. You only employ those words which are known in other contexts. In Aryabhatan system, you cannot do Shugru. There is no meaning. Sugushitrilu. So you can write numbers, but then so it is not something which is used in other contexts. So here you can employ the same words used in other contexts, and you can build it. So, and this Bhuta Sankhya, which I mentioned a little earlier, so this has to do with the general things which are known in the society. For instance, earth, moon, see, so fire, so stars. See, stars, when one says, number is 27. Okay. So mountain, see, they say it is 7 because the famous thing is Yedu Kondalavada. Okay, 7 peaks. Okay, Tirumala is called 7 hill with 7 peaks. Okay, Venkateshwara is described as. So that is how it is 7. So fire is 3, sky is of course 0, direction. So these are all things which are used. And parts of human bodies are also used: eyes, ears, jaws, knees, fingers. So fingers. So all these things are used. So gods. So various things will be used for representing various numbers. So let me just give you one simple example. Khadri Rama Agnayaha. Kha is 0. Adri means mountain. So 7. Rama is 3. See. Ayodhya Rama, Balarama, right? Parashurama. Okay. So Rama is 3. So that is how it is. Agni, as I told you, is Treta Agni. See, Ahavaniya, Garhapatya, Dakshina. So that is 3. So 3370. So Veda, Anka, Chandraha. Anka is 9, Chandra is 1. There is only one moon for us. So Veda, Chandra, Dvi Veda, Abhi. See, so this is how they can use. Bhujanga, Nanda. See, Nanda is used to refer to 9. There are famous 9 famous kings in Nanda dynasty. They have been listed somewhere. So that is how they use this. So that's how it goes. So the readability is something, you were asking, no? So I have come to this. This is the interesting proof of the surface area which Bhaskara has given. Bhaskara in his Leelavati simply presented the verse which I showed you right at the beginning. So where area of a circle, surface area of a sphere and volume. This interesting proof that he gives is in a different context, and it goes with a very nice simile. So that's what I wanted to highlight here. See, he says, you imagine, ये क्या बोलते हैं, gooseberry, amla. Okay, so imagine a sphere like amla. Why amla? Because in amla you will find these lines. You see, so like this lines of longitude kind of a thing. You will find some white things. So this is how you can imagine your sphere to be made up of. Okay. See, Mukha Buddhnaga Rekhabihi Yadvad Amalake Sthitaha. Amalaka is this gooseberry. So this is how you have to visualize your sphere to be. Then Drishyante Vaprakaha Tadvat Pragukta Paridher Mitan. What we usually refer to is this lune. See, suppose you have a sphere, so you can think of various lines like this. So this is called a lune. and this is what is referring to as Vapraka. Vapraka. So in gooseberry you will find this kind of a thing. So therefore he asks us to think of something like this. Okay. So Mukha is this, Buddhana is bottom, Rekhabhihi the line. So you can conceive of the sphere to be made up of various lunes. Here he gives a very ingenious way of proving the result. See, what he says is, for convenience, he says, imagine the great circle to be divided into 96 parts. This 96 is because one quadrant people used to do divide into 24 parts. So this 90 degrees divided by 24 is 3 degrees and 45 minutes. So this is something which has been chosen as a simple unit for some reason by these people. So what he says is, you imagine the sphere to be made up of this kind of divisions. Okay. Then what he says is, you try to find out the area of one lune and then multiply by 96. That will give you the area of the surface. Okay. How do you find out this? He says that this is made up of 23 trapezia on one triangle. Right? As it goes from here, so each one is a trapezia. And you know how to find the area of a trapezia as well as area of a triangle. Just sum it out. So you will get something. Then multiply by 96, that will give you the surface area of a sphere. So this is the idea. So which this person seems to have explained here. See, Drishyante Vaprakaha Tadvat Pragupta Paridhermitan Urdhvadhokrita Rekhabhihi Gole Vapran Prakalpayet Tatra Eka Vapraka Kshetra Phalam. See, Eka Vapraka Kshetra Phalam. Kshetra Phalam is surface area. So find it for one lune. Khandaihi prasadhyate. How do you do? By imagining it to be made up of very small parts. Prasadhyate means you obtain. So you obtain the area of one lune by imagining it to be made up of very small parts. Then there is a nice way by which he makes the sum of it. So which I will just show you. So Sarvajyaikyam Tribhajyardhahinam Trijyardha Bhajitam Evam Vapraphalam Tatsyad Gola Vyasa Samamyataha Paridhi Vyasa Ghatoyam Gola Prishta Phalam Syad. So this is what he is saying. So this is the image. See, this is how one can conceive of the various trapezia and one triangle. So you make the sum. So area of the trapezia, so area of the triangle, so sum 1 to 23, so you get this. So then what happens is, so he just says, you imagine for convenience. See, for convenience you can choose whatever unit you want. The generalization can be done later. So he says, at this, suppose you have a great circle arc. At this, whatever be the distance of separation between the lune, you take it to be 1 unit. So as you move from here, this will keep on reducing, right? So if the radius is r here, so the radius is small r, it will appropriately it will reduce. It's a simple rule of 3. So that is what he is saying. If r is equal to 1, then ri is equal to some xi. So whatever it is, so then it basically amounts to this r1 plus r2 plus r3 and so on. See, if the radii, you start with r, so these are the values. So then, so this r at this point, you can conceive it to be, see, suppose you have the center here, so this r, so this ri, suppose this is ith segment, so this is nothing but your sine value. So it boils down to summing up sines, so which you already know, the sum of sines. So they have already given this table. So you just add that, see, ri is r times sine of phi alpha, and then so the area turns out to be sum of sines minus trijya is basically the radius of the sphere. So you do this, and numerically it turns out to be this. See, so this 2a, this a is one half of Vapraka, this is another half of Vapraka. So 2a is the area of one lune, and this turns out to be 30 numerically, 30 times this, and this is nothing but, see, suppose you take this circumference to be 96 and that will be simply d. So you know the pi value anyway. So since this is this value and this turns out to be the diameter, pi times the diameter, the circumference times the d will give you the volume area of the sphere, c times d. See, so the way they put it is, see, c times d by 4 is the area, so this is pi r square, and they said you multiply this by 4, so c times d will give you the area 4 pi r square. So that is how he simply presents the proof. And this volume also is very interesting. So this the way they have conceived of the volume of a sphere. So you just conceive of it to be made up of n number of slices. Okay, just imagine. So there the division is, see, this division is equal. The length was equal there. Here this slice, okay, so this diameter is divided into equal parts. So that is how they say you divide d by n. So then find out the volume of one elementary slice and then add it up. So this is the idea. So this area of a circle I told you earlier, so how it is conceived of. Now he says this cjth slice, okay, so this will be like this, and the area of that, so you find out the elementary volume of it, multiply by the thickness. See, the point is, so he says just conceive of one strip. So this strip is thickness is delta, and so it just amounts to summing up this. See, I'll just give you the overall structure of this proof. So delta V is this, and the total volume is the summation of all these strips, and this thickness is 2r by n. What we want to get it is in terms of r. So here the only thing that is not in terms of r is this bj. Bj is basically the sign, okay, the small radius, okay. So this is what is bj. Bhuja, they call it bhuja, that is why I have used this word b notation. And for finding this, he uses this. See, we know the product of cards. See, a times p, ap times pb is np times ps, okay. In any circle, choose any card. So this is the rule of cards. So use the rule of cards to obtain this and then sum it up. See, so this is what is called Jyashara Samvarga Nyaya. In fact, this has been stated by Aryabhata. Vritte Shara Samvargaha Ardhajyavargaha Sakalu Dhanushoho. Vritte means in a circle. Shara Samvarga. See, Shara is Vana. So if you conceive this to be the bow, see, in fact, the way they use the terminology to represent, so A, B, C will be called as Dhanus. It looks like a bow. And A, E, C is the card which looks like the string of the bow. Okay. So that is the terminology. They call it as Jya, Guna, Shingini. So they are all synonyms of rope. So the sign will be basically referred to by this. Okay. And the arc will be referred to by, and EB here is like an arrow. Okay. So EB is an arrow. If you conceive ABC to be the bow, EB is arrow. If you conceive ADC to be the bow, then ED is arrow. Okay. So both of them can be conceived as arrows depending on where you draw the segment. So therefore he says Vritte in a circle, Shara Samvargaha. The word Samvarga is product. Okay. Varga is square, Samvarga is product. So the product of the arrows is equal to the product of the sign. Okay. Ardhajya vargaha sakalu dhanushoho. This is how the rule has been stated, and you employ this rule, so you will immediately get. See, so this I am just writing bj square as ap times pb, ap times pb, and this can be written as np times ns, and so this you rewrite like a plus b square kind of a thing. So once you do this, you will straight away get it in terms of r. See, np plus sp is 2r, and this square, basically you have to sum up, see, from 1 to n. So when you make this sum, this np is j times the delta, okay. np is j times delta, and sp will be n minus j times delta. So if you want to square this and that, so it is as well taking 2 times np square, okay. So straight away from this you get this. So this boils down to 1 square plus 2 square plus 3 square for large n. So this whole problem boils down to, in fact, the proof of the other thing also. So this is a very interesting that these people have done. Making an estimate of the powers of natural numbers for large n. This they have very systematically done. So that is very interesting. I don't think I will have time to get into the details, but it is a very nice way of arguing this. So 1 square plus 2 square plus 3 square, so it is going to be n cube by 3. 1 to the power of k, 2 to the power of k, 3 to the power of k, n to the power of k will be, so n to the k plus 1 by k plus 1. This is a general rule, and they have very systematically shown that, okay. So this actually is the most important thing. In fact, when we try to show, so when we try to explain students y integral x to the n dx, okay, x to the n plus 1 by n plus 1. So the discrete equivalent of this is this. So 1 to the power of k plus 2 to the power of k summation I to the k, so is nothing but up to n is n to the k plus 1 by k plus 1. So this is how actually, if you look at the basic text on calculus which explain the foundation, so it goes like this. So this is one result which the Kerala mathematicians have systematically arrived at, and once you have this in place, you will be able to prove. See, the way they have done is, so you do some algebraic manipulation, bring it to sums of powers of natural numbers, and once you do that, so that is our basically the integration kind of a thing, okay, for various things. So this is known, and therefore you straight away get the volume of the sphere. And I mean, last 1 or 2 slides, I wanted to tell you how they employ some nice examples to demonstrate a particular rule which you give. For instance, they wanted to give some illustrations for solving this quadratic equation. So here they choose an example from Mahabharata. He says, Parthas karnavadhaya marganaganam kruddho rane sandadhe sasyarthena nivarya tacharaganam mulais chaturvirhayan shalyam shadbhihi atheshu bhistribhirabhichatram dhvajam karmukam chichedasya shirasharena katite yan arjuna sandadhe. He says, the Partha and Karna, so they were fighting with each other, Karna and Arjuna. So he shot a certain number of arrows. Margana is the word which is used to refer to arrow. So this is a very nice word. See, Margana is that which searches the path. It is like missile. You understand? So that which goes and hits something. So you say that this has to go in this direction. Marga. Margana Gana means a group of arrows. Okay, heap. So shower of arrows. Kruddho rane sandade. Then he says tasya ardhena nivarya tachara ganam. So this fellow n by 2, suppose it is n. So they two collided with each other and then fell. Okay. Then he says mulais chaturbhihi hayan. So then he says mula is square root. So then he killed the horses of that fellow. This incidentally is building a story and making it interesting for the children is one aspect. The other aspect which one notices in this story is how a warrior has to handle the other fellow. So you initially try to finish various other things, leave the fellow alone. If he surrenders, then you leave him. If not, then you finish him. So that is how it is. So the whole thing basically is a description of that. See, he chopped off the flag hoisting, then he chopped off the umbrella. So then he finished the charioteer. This fellow was left alone. So that is how he goes. Finally, chicheda asya shiraha sharena, with one arrow. tell me what is the total number of arrows which Arjuna shot. So this, if you try to put it in mathematical form, this will turn out to be a quadratic equation, and the solution, it cannot be negative, therefore it is 100. Okay. So this is how they illustrate the formulae which they use. So finally a few observations. So only a fraction of this is known in the West. Too many people still think that mathematics was born in Greece and more or less slumbered till Renaissance. Okay. So this is how it is not known. The contributions of other civilizations is not so well known in the textbooks on history. So it is changing slowly. What is the problem that is involved? So I just recently I had been to New Zealand as a visitor. Then we were reading some of the manuscripts in original. So this is how they are. This is one of the best manuscripts. So this is how they are written down in those days. See. So for instance, I will read you. Try to read some place. So which I have already read. Therefore, see. See. So let us start from here. Here a previous verse ends. See. Kakha gagham bhumi taleshu mandalam. You understand? Kakha gagham bhumi taleshu mandalam nakendrakam karkatakena sadhayet. Kacham chacham chapa yugam kangam changam kramat vyasadalattrayam likhet. So this is how actually it is very difficult. So people who have done the edition of this manuscript, so we have to really honor them for the kind of trouble that they had taken in trying to decipher and present it in some readable form. So it is actually quite difficult, and we have to have some 2-3 things. So this, but it is quite fascinating and extremely challenging and also rewarding. So this is something which I can tell you. So based on some sort of studies that I did, and this is something which I chose from 17th century. What I found here was, so the kind of scholarship that has been developed from the time of Aryabhata in trying to put various things in versified form has definitely been maintained till recent times. So these verses were really amazing, and some of the illustrations that he had given as to how one can demonstrate certain principles, so are quite wonderful. And sometimes you will find manuscripts like this. So these are palm leaf. That one is a paper manuscript. This is far more difficult to decipher. So one thing which we need to find some solution is to see that they are not lost. In many places they are getting lost. Okay? So in various places people try to value them and sort of preserve them. But here unfortunately, so we have not been paying so much attention to preserve them. For instance, this work I found it very interesting. So had nobody cared for maintaining this, so it would have been completely lost. So there is a different way of presenting something. So those are all very important. So what is to be done? So I will just end up my lecture with this. So Manjul Bhargav, he says students in India should be taught about the great ancient Indian mathematicians like Panini, Pingala, Hemachandra, Aryabhata, Bhaskara. So he starts with Panini, Pingala, so which is like 500 BCE. So and then he lists till 12th century, and of course later, so we have various mathematicians. So these stories and works inspired me, and I think they would inspire students across India. Many of these works are written in Indian languages in beautiful poetry. These Indian languages is very important. See, it is not only Sanskrit. So there are certain works which are in Tamil. There are certain works which are in Kannada. So there are certain things which have been developed. So taking inspiration from Sanskrit, I mean, it may not be able, one may not be able to convey with a double meaning. Double yantandre may not be possible, but definitely certain very interesting examples in different kind of rhythm, so which the local languages have. So attempts have been made. See, if you do that, so then I would say that, see, today, I mean, there are thousands and thousands of books on electromagnetic theory which are being written. I mean, the substance may not be different. Presentation may be different, and something may be much better done there. And so too, I think there is nothing wrong in trying to promote these kinds of things in different forms. So that will actually improve the language skills of the people. So some creativity can be generated in the society. So all these aspects have to be considered when one presents these things. But somehow, I mean, we have sort of ignored most of them, and we only feel that this is the only notation which has to be employed. This is the only set of axioms with which one has to begin, kind of a thing. So I think it may be better to inspire students through these kinds of things, and this may be a little more interesting also, this way of teaching mathematics, rather than simply so asking them to memorize formula and then without showing them some applications. Thank you.